That is very easy. It's just a simple thing. We'll put it in our notes today. No mechanism, thankfully. But the final reaction for us, yay, is ozonolysis. Ozonolysis comes from two words, ozone, which is O3, and lysis, or cleaving. And we can take alkenes, let's go back to this kind of more simple alkene. And if we treat them with O3, step 1, step 2, well, we can use dimethyl sulfide. These are the conditions I'll teach us. There's other in the text, and you're fine. But this is the one I need us to know this semester. What this reaction does, it actually cuts this bond right in half. And it does something useful for us in the second semester of this course. It gives us an easy way to make carbonyl-containing compounds, or compounds that contain a carbon-oxygen double bond. The function group on the left is called a ketone. It's where we have a carbonyl group with carbons on both sides. And if we only have one carbon on one side and a hydrogen on the other, it's called an aldehyde. The function group is called carbonyl. Most important function group in the second semester of this course, probably the most important function group in biochemistry and all of biology, is the carbonyl functional group. So ozonolysis, it's a little bit tricky, but for us we just need to know the conditions, cuts it in half, replaces things with oxygen. Let's take a different example here. By analogy, I'm going to leave you for a moment to draw what you think the products are in your notes. We're going to take this particular alkene. I want you to draw what are the two ketone-containing or carbonyl-containing compounds that you would get from this. We'll do one more after this too, so work on this right now. I'm going to draw another problem in here for us to practice, so you can get the hang of this one really quickly. There's nothing to this type of problem. In this first problem here, I've left with you, you should be cutting it in half right now and installing oxygens in those two places where the double bond was. Just follow this pattern that's in the top one. The bottom one starts with a ring. The clue is it's going to cut this bond in half and install carbonyl groups in place. So try and fill in what belongs here, here, and here right now. Normally I'd have you work with a partner now. I'm sorry we can't easily do that quickly in Zoom. So instead, work on your own. Draw things. Going to be asking you drawing things Thursday, so this is a great moment of personal reflection. Do you feel confident drawing things? Do you have a strategy to tackle this problem? Can you look at some patterns and say, well, if I see this one do this, then this one should do what? Well, if this bond cuts in half, then we should be drawing and have to make sure we bring all our carbons along. There's 1, 2, 3 extra carbons. We can check our work. On the left side of the alkene, there's 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. On the right side, there's 2 carbons and a hydrogen. So this is what we should get on the right side of the equation. Down here, so yours might look a little different than mine. They might be an all stick drawing, they might be an all expanded drawing, they might be in a mix like I've done it here of stick and condensed. It's okay if you have something drawn slightly different, as long as it's the right number of carbons, right chemical structures. A lot of variety here. This particular one, we're going to basically break this bond and put oxygens in place, but our ultimate product breaks apart, but it's still tethered together by a chain of CH2, 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 CH2. So if you're really struggling with this, try it again. So give you just a 10-second head start. Yep, Jennifer, it's absolutely okay if you don't write C in the products. Perfectly acceptable. While you guys are working on this last one, I'll rewrite these two particular products in a slightly different way that maybe some of you wrote them. Okay, so all of us mere mortals can keep working on this, but I'll make some equivalent structures here. You don't put the electron pairs in these, it's okay. Aldehyde, technically you don't draw the H in, but some people do draw the H in, that's okay. But these two things are absolutely 100% equivalent. Some of you might draw on something different, even with writing CH3, CH2, CH2, that's okay too. So hopefully that's what you were thinking, Jennifer, here. I suspect it was. But just as long as you represent the right number of carbons, this one has 1, 2, 3, 4, 5 carbons, so it means the same as this, and it clearly is the right number of carbons on the left side of this alkene. Okay, enough yip-yapping for me or chit-chatting here. I'm going to actually do the problem. Maybe this one's a little tricky to come up with a way to draw it nicely. I hope some of you came up with something that looks like this. Maybe some of you came up with something that looks like this. These two things are 100% equivalent to one another. Okay. So this is what happens when we have a ring with an alkene in it and treat it with ozonolysis. It's only the double bond that breaks. So a little bit more challenging here, but no need to panic. Don't ever panic when you see a ring in an organic chemistry problem. All we're doing in the past 2 days is fixated with laser sharp focus on alkenes. These conditions don't do anything to this carbon, hydrogen, this carbon, this carbon, this carbon, or this carbon. They just do something special to the alkene. So the methyl group stays, the hydrogen stays. The CH2, the CH2, CH2, CH2 groups all stay the same. They're the same things here. Hydrogen, methyl, CH2, 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 CH2. That's all the same. The only thing that happens here is that the alkene pops in half. Okay? So, luckily for us,